Good afternoon, everyone. It's great to see you again. Thank you for joining for another edition of RAS International Webinar. My name is Nicola Cobiello. I'm hosting it in front of RAS from Delft University of Technology. And today we have a great pleasure to welcome Giorgio Medeossi, Nicola Cobiello, and Thomas Nygren from Italy and Norway. They will be talking about a very hot topic on putting simulation and optimization algorithms into practice and solving some real life problems and how we can actually do and what we can benefit. So Giorgio and Nicola, they have both PhD degrees in railway operations, and Giorgio co-founded a company called TRENOlab in 2015, and now already involved in various projects around the world already. So I believe they will have lots of great information and details to share with us. So to give you a bit of an outline of today's webinar, basically we'll have the presentation of about 35 minutes. All the questions that you may have also during the presentation, I encourage you to put them in the chat during the presentation as well. And once the presentation is done, then I will read out the questions to Giorgio, Nicola, and Thomas. So chat would be preferable. And then if you really would like to say something, then we can go for a mic. You can then raise your hand. And this video will be recorded and it will be shared afterwards. So I would now invite the guys to share the screen and to kick off the presentation. Nicola, you need to turn on the mic.
Okay. You should now be able to hear me finally. Okay. Hello, everybody. I'm Nicola Cobiello. I'm a research engineer at TRENOlab. I will in some way guide you into this presentation about our way to automatically generate and simulate railway timetables. In order to start, I will just have a look of the outline of our presentation of today. We will start with a glimpse about the strategic network planning in Norway and on the related research. Then we will go on and describe the solution we proposed for tackling this problem, that is a multi-objective colony optimization algorithm. And then we will pass to see how this algorithm and the related tool is integrated in our TRENO suite for timetable planning and simulation. And then we will end with a real demo about our tool. So I will pass my voice to Thomas from Urban Directorate, who will introduce us in the world of strategic network planning in Norway. Please, Thomas.
Thank you, Nicola. I work at the Norwegian Railroad Directorate called the Jernbanedirektoratet, and we are responsible for the strategic network planning of railways in Norway. And when doing that, we base our work on market demand, requests from municipalities, from the counties, from the government. And of course, we also have to consider the constraints of the existing or otherwise planned infrastructure. You can click one more, Nicola. And our first step is that we create what we call service concepts. This is a part of that for southwestern part of Norway, one of the possible future service concepts, describing basically the stopping patterns, the number of trains, and additionally, not given in the figure here, running times, the type of rolling stock, quality of service, etc. Then we have to work quite a lot to make that into a timetable. We have to calculate the necessary stock of rolling stock that we need to run it, where they should be stabled, etc., and also what infrastructure changes that we need to make in order to make that service concept feasible. And then we have to pass that on from my department doing strategic timetabling and capacity studies to the socio-economic department who do the transport modeling and cost benefit analysis. And then we have to decide if we can implement that. One more, Nicola. Or if we have to do another iteration. And quite frequently we see when we reach this cost benefit step in the more detailed output there, that there were improvements we could have done in an earlier phase that would have provided possibly a better result in the end. But then if you move to the next slide, this strategic timetabling work, which was the sort of bottom right part of the previous slide, is a very time-consuming part of our process. It requires skilled timetable planners, of which there is a limited supply. And even medium-sized strategic timetabling projects normally take several months of this timetabling work. If we have the larger projects that we do for the every 4 years national transport plan, this is a project that takes a couple of years. And it's a mix of very high-level decision-making and low-level puzzling, to be frank, to a bit of creative puzzle work to make a timetable possible. And what we see is that the more of this low-level work that we can automate, the better we can use our planners. And actually, we can also be able to do this. We can deliver better results in less time and actually study more alternatives than we can when we have to do all this detailed grid work ourselves. So next slide. We started in 2014 a cooperation with SINTEF at the time for a first pilot study of using mathematical optimization to generate railway timetables on mixed traffic single track lines. So both freight and passenger services operating on our test line, which was the line from Oslo to Gjøvik, north of Oslo. We followed that up with a new pilot in 2018-19, again with SINTEF. And now we are currently undergoing a project with TRENOlab and their subcontractor University Gustav Eiffel, which we will present some results from today.
Thank you, Thomas. So let's go into the very kernel of our topic, and let's describe the timetabling algorithm we propose. We moved from a very, let's say, basic intuition, that is, our algorithm try to mimic the real practice that is performed by a real timetable planner. When we design basically a timetable, we iterate two basic actions. That is, at first we choose the next train or the next periodic train group to be scheduled within a given set, knowing that we possibly have some trains or some train groups which are optional. So we would like, in principle, to schedule them, but if we are not able to find out a proper arrangement within a timetable, the timetable will be still valid. So at first we select one train or one train group, and then we actually schedule it within that timetable, which is possible already populated by other trains, by trains we have already scheduled before. We repeat this pair of action, and probably we get to a point in which we have scheduled all the trains. So we go back, we look, we search for a train group which is not so promising, which we don't like it very much. We remove it from the timetable and we schedule it another time. And we iterate this couple of actions until a convincing timetable is found. So we translate this concept into the ACO terminology, let's say, but we translate it with a multi-objective perspective. This is due to the very nature of this project. We remember that we are dealing with strategy timetabling, and during strategy timetabling, we would like to assess not just one timetable, but probably a range of promising timetables. Promising under the point of view of a set of KPI that are our actual objective functions in our algorithm, that in our case are the total travel time, the total energy consumption, the resulting timetable stability, the number of scheduled trains in case we have optional trains, so trains that we can decide whether to schedule or not, or in some specific case, the number of residual conflicts. If we allow, we relax the conflict constraints, so we allow the resulting timetable to feature a certain number of residual conflicts. So we run the algorithm. The algorithm would finally provide the user with a Pareto optimal set of feasible timetables rather than one single timetable. So in this way, the user, the timetable planner, could have a more complete overview about the possible way in which variable capacity is used on a given infrastructure. Let's recall some fundamentals about ant colony optimization. Ant colony optimization is a myth-heuristic, so it's not an exact algorithm, but a stochastic one, which mimic the behavior of ants, which in nature are looking for food, basically. First of all, we have to model our problem in terms of a graph, which is called a construction graph, in which each node is a solution component. The feasible solution of our problems is therefore a set of nodes in this construction graph, and can therefore be seen as a path or a click in this construction graph. The graph structure allows us to build a feasible solution as a incremental process in which we choose a node, then according to a certain ratio, we choose the next node, and so on. This certain ratio is guided by basically an heuristic factor, which is an estimation of a desirability of choosing a certain node with respect to the other candidates, and a pheromonal ratio. Pheromone is a sort of memory which is stored on the construction graph. After each iteration, the best performing ants are selected, and on the solution, so on the path found by these best ants, a virtual pheromone is laid. This virtual pheromone is just a value which characterizes an edge or a node on the construction graph. In this way, we can memorize, we can record which are the best found solutions so far, which can possibly guide the next iteration to be performed. Just a couple of words about the infrastructure and the operation model we use to generate timetables. We use a macroscopic model to this purpose. Our infrastructure elements are nodes and edges on an infrastructure graph. Each node or edges are characterized by different values, which models the infrastructure between rolling stock, the interaction between rolling stock and the infrastructure. Namely for line sections, so stretches connecting consecutive stations, we introduced the minimum technical running time and the minimum headways, which characterize the running of a certain type of rolling stock on that line stretch, alongside the maximum energy consumption associated to the minimum technical runtime. On the other side, in station, we consider the variable tracks that given rolling stock can use, as well as additional runtimes due to the utilization of station track different from the main one. On this kind of infrastructure model, we then define our timetable model, which actually represent the service concept we would like to schedule. We start from a desired, let's say, path, and around this desired path, we define an admissibility range in time and space, which denotes the part of the time-space plane in which that path can be designed, can be actually scheduled by the timetabling algorithm. So we introduced for each station the minimum maximum stop allowed stop time, whether a stop is mandatory or could be optional, or whether a pass is mandatory, the minimum and maximum allowed runtime, which are both greater than the minimum technical runtime, and the minimum and maximum values for the arriving or departure events in each station. And finally, also the usable tracks for each train in each station. So let us pass to the description of our multi-objective ant colony optimization algorithm. If you remember the first slide I showed you, I said that the timetabling process is basically constituted by the iteration of two basic actions that are the choosing of the next train or train group to be scheduled, followed by the actual scheduling of that group inside an already populated timetable. So we implemented a 2 layers architecture for our ACO. These 2 layers exploit 2 different construction graphs and implement a multi-colony architecture in order to perform a multi-objective optimization. In the first layer, we actually perform the choice of the next train group to be scheduled, or just in case of optional train groups, whether to schedule or not that train group. In this simple example, we have 4 groups. 3 are movable, so are groups which must figure in the resulting timetable, but are left free to vary by the scheduling algorithm. And 1 movable optional train group, that is a group which can deactivated by the scheduling algorithm. We use 2 kinds of heuristics for guiding the choice of the next node to be chosen in this graph. These heuristics actually model the train's priority and the conflict probability with the already scheduled ones, already scheduled train groups. So let's see that, for example, we start for let's say that we have just scheduled the group 1. The next choice could be to one of the nodes which are highlighted now. Let's say that the algorithm chooses the second node and then pass to a third node. And the choice is guided on one side by the pheromone laid by on the relevant construction graph edges, but on the other side of the 2 heuristic factors which I mentioned before. So for both node 3 and 4, the algorithm actually consider how many additional trains the scheduling of a certain group involves, and how much conflictive this possible next group would be with respect to already scheduled trains. And so the choosing of the next node proceeds in a stochastic way. As soon as a certain train group is chosen for the scheduling, it is scheduled by in layer 2 that we will be soon. Finally, a solution in layer 1 is a click. It's not a path. So a set of nodes and the set of all the directed edges connecting these nodes. On this click, which is a solution on layer 1, the pheromone will be laid at the end of the iteration in case of the relevant nth is chosen as a best performing one. We mentioned that we used 2 layers. So we will see what happens in layer 2. Being an ant colony optimization algorithm, also in layer 2, we deal with a construction graph, which is conceived as follows. We consider for each train to be scheduled a journey, so a sequence of stations and line section to be used. In this case, for example, we have a journey composed by just 3 stations. We report on the space-time graph these actions. We have 2 virtual start and end events. And then in order to be able to build a graph is composed by nodes, so by discrete items, we have to discretize our continuous variable, that is time. So with that discretized time, and we start to define for each station and for each our departure or arrival event in station, the relevant event node. So for station 1, so the first station of the journey, we define a certain number of nodes representing departure events taking place at a certain track, at certain time, and with a certain stop or pass behavior of the train in that station. And we continue in this way for the following station. So for station 2 and track 1, we have the relevant set of nodes, as well as for departure from station 2 in track 1. But we have the same for station 2 for track 2, which is another track usable by that train in that station. And we keep on building the construction graph in this way until we reach the end virtual node. Then, as you can see, we introduce the variable stop timing station or run time in line section by having several edges exiting a single node. In this case, we model in station 2 a stop time which can vary between a minimum and a maximum value, as well as a run time which can vary between a minimum and maximum value in a given line section. Then let us introduce another topic, that is how we deal with already scheduled groups during the exploration of these layer 2 graphs. So let us assume that we are scheduled the train number 3, having already scheduled the trains 1 and 4. For train number 2, in this case, we choose to not to schedule it. So we have to deal with an infrastructure which is already occupied and utilized by other trains. This means that some nodes and edges are conflictive ones. So we, in principle, should avoid the utilization of these edges by train number 3. In this case, we notice that some conflict-free path can be found in this graph. So in this case, we limit the exploration on layer 2 graph performed with the stochastical, pheromone, and heuristic guided ratio to the path with the minimum number of conflicts, which in this case is equal to 0. So probably the possible behavior of the and search on this graph could be the following. They start from the root node. Now they have 2 alternatives, other 2 alternatives, and so on. But we notice that the ants are restricting their search to conflict-free nodes. But we could have the case in which the already scheduled trains involves such a high infrastructure utilization that no conflict path exists. In this case, we limit the search of the ants to those edges belonging to the path with the minimum number of residual conflicts. So we basically, we have as the result of the multi-objective and colony optimization algorithm a Pareto set of timetables which are not necessarily conflict-free. So there could be timetables with residual conflict. If the user wants absolutely to deal just with conflict-free timetables, we refine these the timetables produced by ants with a mixed integer linear programming formulation. This mixed integer linear programming formulation implements conflicts as hard constraints, and therefore it produces only conflict-free solutions. If no conflict-free solutions is possible, it returns an unfeasibility. On the other side, the MELT formulation further improves the values of the other objective functions by exploiting two facts, which is basically the nth discretized time. So they introduce some degree of granularity or resolution in the problem, while the MELT consider time as a pure continuous variable. And on the other side, the nth enforce strict periodicity between train of the same periodic groups, even if a certain degree of tolerances could be allowed. For instance, we could allow trains belonging to the same groups to deviate from the strict periodic grid of maybe 1 minute in certain station. This could be very useful in order to reduce residual conflicts, as well to improve the objective function values. The MELT formulation actually exploits these grid tolerances, let's say. So in order to conclude this overview about the multi-objective and colony optimization algorithm, I will show you the overall architecture of the algorithm framework. So basically we have two parts, one relevant to the end colony optimization algorithm and the other relevant to the MELT formulation, which is solved by a commercial solver. In our case, we are using Gurobi. You can see that the MELT formulation could be used for two purposes. The first one is to actually refine the whole Pareto optimal set provided by nth, but on the other side, it can be used as basically a local search to improve some solutions found by nth within the iterations of the end colony optimization algorithm. So we can figure out a lot of utilization combinations that are still under extensive testing in order to find out the best way to utilize this framework. So I will pass the lead to Giorgio, who will.
Thank you, Nicola. Okay. So we now go a level up or down, depending on how we see it, and we get to look at how the ACO tool is integrated in the other existing tools that we use. We have the ACO tool, we have our conventional planning tool, TRENOlab, and we have our microscopic simulation tool, TRENissimo. These three components of the suite work perfectly integrated with each other, so that the user does not have to move files and can follow all the steps in a very comfortable way. The first step of the process is, as mentioned by Nicola, is to prepare the service concept, which is done pretty easily in TRENOlab. Once this is prepared, click and click exactly, the TRENOlab runs utilizing the microscopic model in TRENissimo, runs the running time, headway time, and so on calculation that we will see in a moment. The service concept and the running times and so on are pushed to the ACO tool, which is run, and a set of timetables is obtained. Among this set of timetables, the user can decide whether to import the preferred one or to import any of the other drafts. They are compared graphically. All the KPIs are displayed in an easy to understand way. So the user, the planner, can decide which seems to be the best and push it back to TRENOlab, where the timetable can be edited as in a conventional timetable planning tool. And from there, it can be pushed to the microscopic simulation tool for a final global validation and robustness test. A bit more of attention in just 2 points. First is, how do we get the running times and the headway times? We don't get them from a book, we don't get from regulation, we don't get them from a macroscopic model. They are calculated based on our microscopic model that is integrated in TRENissimo. So once the one more click, the service concept is available, let's say the TRENOlab is able to construct the microscopic routing for all trains on the entire network. One more click, Nicola. And to compute their running and headway times. With one more click, we go in more detail. So what we calculate is, as required for the algorithm, not only one click, the running times and blocking times of trains on their default itineraries, but also the time losses and the blocking times in event we want to make these trains use an alternative itinerary, an alternative platform, or to insert an additional stop for trains, of course, that would accept additional stops, such as typically freight trains. Third, still based on blocking times, we calculate the headway times for all sequences of trains on all line sections of our network or test areas, based on the blocking times and thus on the same microscopic model. With one more click, so we are ready, and we have the the ACO tool ready to run. We run the algorithm, and we will see it in action in a moment. But we focus once more around on the microscopic simulation, which is used for verifying that the timetable is robust. TRENissimo is a state-of-the-art simulation tool designed, let's say, based on the experience of its predecessors to be more intuitive, accurate, and flexible. In particular, we say that it is accurate because trains are driven by a real, let's say, dispatching system, because there is an explicit representation of the driver behavior. So we can really decide what does the driver do when it spots a restrictive signal aspect, a double yellow, a blinking yellow, and so on, depending on the country, because we can use as input the delays and dwell time distribution taken directly from real data, and because we opted for an explicit, again, representation of signaling system. So from the graphical icon and the animation of signals to how they are reproduced in the model, for each country, we implement natively its signaling system. We say that it is fast because animation and calculation are separated, because we take advantage of multi-core computers, because we don't need to open any graphical element, and because we can run multiple simulations on multiple computers in parallel. So if you have, let's say, 10 8-core computers, you would run 80 runs in parallel seamlessly for the user. In the end, it is efficient because, as you have seen, you don't have to create the microscopic routing from the macro timetable. There is an algorithm that creates it for you. In 1 second, we will see that, let's say, TRENissimo, there is a TRENissimo model available for the entire Norwegian network. 24 hours of simulation of it run in just 6 minutes, including all train runs, all freight movements, all empties, and so on. And the next slide, we briefly see the tool in action. Here we are on the Bergen line, connecting a long single track corridor, connecting Bergen with Oslo. Here, scrolling, you see that we have all lines of Norway. We can open any of them and we will see trains running on any of them. This is now the graphic timetable updated during the simulation. The simulation is slowed down and we now accelerate it a bit. So we see that it can be, say, much faster. We now slow it down again and change area and go briefly to get a look at what is happening now at 6 p.m. at Oslo Central Station. 2 clicks and Oslo Station appears. Let's pause it. Let's get a look in more detail. What is this train doing? How much is the station utilized? And we see the actual track occupation diagram with blocking times and occupation time being generated live. We can get a look at which are the most critical signals. We are in Norway, so trains don't run on the left, but on the right. So let's get a look at the signal. And here we see the log of the aspects seen by that signal. You see a huge number of trains utilizing this signal. It's one of the most utilized in Europe currently. 2 clicks on a train to see what happened, to get a look at its speed chart, and then 1 more click to get to create the graphic timetable for the train. We might also very easily identify the most critical trains on the network. We've said that we have a good timetable, but it is never perfect. And with this list, we can easily check which are the most critical, the most delayed trains on the network, double click and see what happened to that train. In this case, we see that it had a horribly long dwell time. It's a freight train that had to wait almost 1 hour. If we go with the mouse on over, we can see the cause of its delay. Okay, in a final view, but I'd let Nicola continue. We also see, let's say, how crossings on single track lines are managed, which is one of the obviously key elements of operations in a country like Norway. This is how trains are conveniently and realistically dispatched there. Back to you, Nicola.
Thank you, Giorgio. So now we will conclude our presentation before drawing our conclusion with a very quick live demo of the whole process. Let's start with the definition of the service concept, which is performed within TRENO. This operation is very easy, since we just design some kind of desired timetable. So the ideal timetable we would like to have as an output of our tool. So we define a certain number of paths with their stopping patterns and their approximate location around the day, the operational day. Then, by proper interface, we define the admissibility regions of each train group, and with a very simple click, the tool will take care of calculating every runtime and headway for the infrastructure we are going to use for our timetabling process. And we can find all the calculations data stored in a proper database for which regards headways or minimum technical runtime. Of course, this call for having previously defined a microscopic model for the concerned infrastructure, which should be properly synchronized with the macroscopic model in TRENO, but this is actually this is automatically performed by the TRENO suite itself. Once we have our data set ready, we can invoke the timetabling algorithm. So I will just start it. We can monitor the process by means of a proper graphical interface. Here you can see the Pareto fronts evolving through the iterations within the multi-objective timetabling algorithm. Here we have just two objective function activated, that is the minimization of the number of residual conflicts and the minimization of the additional travel time of trains due to crossings. We can also monitor with in a different way the evolution of the timetabling process within the multi-objective automatic timetable generator. In this case, you can see the actual timetables produced by the algorithm and how they vary from iteration to iteration according to the best solutions found by the algorithm. You can see that the algorithm will actually focus around some best paths, while other one which probably result suboptimal are discarded along the iterations. This process will take time. Of course, I will not wait now 15 or 20 minutes to be performed. So we will actually go to the actual output of our timetabling tool. Here we can see the whole set of generated timetables, which are all conflict-free because they have been refined by the merged formulation, and they can be classified according to different KPIs, in this case, according to the additional total travel time and the number of trains. This is an example in which we performed the saturation with freight trains of the Bergen line in Norway. So if you see on the bottom left, you can see the resulting Pareto set and how different timetables correspond to different points in the objective function space. Now, these timetables can be exported back in Treno in order to be further refined by manual operation of a skilled timetable planner. And when we export them back in Treno, we can also compare the actual scheduled timetable with the, let's say, desired ones, with the service concept the planner initially defined within the suite, which is in this graph is represented by dashed lines, while solid lines represent the generated conflict-free timetable and solution. And finally, last step, we can test the generated timetable for robustness within the Trenissimo, so the microscopic simulation software. It can be with a couple of clicks exported from Treno to Trenissimo, and then a simulation can be run. So now you should be able to see live how the frame paths are automatically calculated by the microsimulator. But this is not happening. So, oh, yes. A little of delay, probably. Of course, after simulation, KPIs can be driven about a posteriori stability, and so we can get a better knowledge of the behavior of the generated timetables. Okay, so from my side, it's all. I will maybe if Thomas would like to draw its conclusions. Or I will do it, Thomas, as you prefer.
Yeah, you can do this, and then I can do the slide that I had afterwards.
Okay. I think that we have no slide afterwards. I'm sorry.
Okay.
But okay, we will probably we already agreed about the content. So we now have a working prototype of automatic timetable generating tool, which is very strictly and seamlessly integrated into a commercial suite. This accomplish the aim which we propose ourselves at the very beginning of the project, which is to create and test a timetable scenario within 1 day. Just just as an example, on the Bergen line, we generate timetables for 3 infrastructure and 6 service concepts variants. So total 18 scenarios in 8 hours. We ran it overnight, basically. On the other side, and this produced more than 250 optimal timetables. So next steps in this research is surely to improve the algorithm performance, which the algorithm is novel and quite original, so it can be surely improved. But on the other side, now we have a very huge number of timetables available, which can be hardly be analyzed by hand. Let's say, okay, we have some Pareto set representation which can help the planner to choose the best timetables to further investigate, but this task could be better helped by probably bulk analysis method. On the other side, we can implement the utilization of other KPIs as objective functions for the timetabling algorithm. All these steps should be, of course, tested by real-life use and validation. So, Thomas, if you want to add something.
Yeah, maybe we can switch. If Nicola Besinovic, if you could make me a co-host as well, and I could share from my screen then the slide that was not, that slipped away.
Yeah, so I can do that, but also we got quite a lot of questions and like just 5 minutes. So would you prefer then maybe to jump to questions instead? Or if you can go quickly through and then...
Yeah, we could. I could just describe the content briefly. From
you can share the slide if you want.
No, but from our side as a public agency, we would really want to. Our vision here is to continue this development and move from the planning cycle that I described earlier, that takes at least some weeks, to a planning cycle that we can do in a day. So at sort of the morning meeting, the boss asks why didn't you consider this or that? And instead of saying, yeah, we can find that out for you next month, to be able to say we can find that out for you tomorrow, and complete that full loop, and actually then be able to also study alternatives that we now would have to discard or disregard because of time constraints. I don't know, Nicola, if you want to elaborate on Giorgio Sartor's question, but basically we are building here.
Do you mind? I'll take care of it. So thanks, Thomas.
Yeah.
Yeah, thank you guys for a great presentation. So we have quite some questions. So one is indeed from Giorgio, and he's wondering a bit on a technical perspective. So what milk formulation you have used? If you could say a few words.
Here we are
yes.
building upon the Bender formulations used in the previous pilots. I don't know if Nicola Cobiello want to elaborate on that.
No, nothing to add. The point is that we use this milk formulation, but with the important thing to focus is that we restrict its application in a very neighborhood of the solution found by ants. So the resolution of the formulation is really quick, and this is the reason we can apply it to the whole Pareto set, to the solution of all the Pareto set found by ants.
Okay, and maybe to follow up on that one, basically you have your ant colony optimization model. What I wonder is, does it, so how do you get from solution that has conflicts as output there to the actually conflict-free solution with the MILP model? So could you maybe elaborate on that one? Or maybe that's just I missed in the presentation, something.
The passage is, we basically, in the ACO environment, conflicts are treated as soft constraints. Basically, the number of residual conflicts is an additional objective to be minimized. We did not explain it into the presentation, but there, within the ICO, a couple of mechanisms which privilege solution with the lower number of conflicts are implemented. So let's say that the minimization of conflicts is it's a privilege, prioritized objective with regard to the other ones. But then what it is important is that a solution from ants which features residual conflicts could be feasible or unfeasible in the milk perspective. So not all solutions provided by ants could be translated into a conflict-free solution by the milk formulation. This is true, but on the other side, okay.
Yeah, and maybe to go to our next question. Well, before we go to the next question, I would like to say that, well, it's 5 p.m., at least on my side. So formally, we are getting to the end, but Giorgio, Nicola, and Thomas were super sweet to actually stay longer. So, and everyone who are willing and free to stick around longer, you are more than welcome. So we have some more questions that they may be interested still to answer, but if you want to drop in and say hi to the guys, all is possible. But for the ones that have to rush to other meetings or breakfast or dinner, thank you all for joining, and we'll share the slides and the recording afterwards. Yeah, thanks a lot. And guys, if you don't mind, I would drop you another question. Okay, so one question that we got from Ricardo is, so Thomas, you mentioned that you want to shorten the planning cycle to 1 day. So then how does that relate to train operators? Because they shall be involved, and so to deal with their rolling stock and crew planning.
our use case here is primarily for strategic planning. So 5 to 15 and even more years ahead in time. So there will be ample chance to do the final touches on that before it's actually put in operation. But rolling stock circulation is actually one area where I've seen that we have some room for improvement, and that it's important to actually integrate that into our tools more to make it sort of make the final mile, because we see that if we have a less than optimal rolling stock circulation and we have to add rolling stock, that is extremely expensive. So it hugely affects the cost of something that seems like an optimal solution. But then if we have to add, we might have to add in something in the scale of like 100 million euro in rolling stock if we just have to add a double train set each direction for something to work. And of course, that will hugely affect the cost benefit analysis. So integrating rolling stock, of course, explodes the complexity of the problem. We are basically colliding two optimization problems together. But I do really hope that we can see that done in the years to come. But that's future research.
Yeah, great. Maybe to follow up, we got a question on testing a new infrastructure. So particularly, you mentioned the strategic planning. So then I could imagine that the infrastructure could be one of the things. So then how easy would be then to test an upgrade to double track or extra platforms? So would you then run the model again from scratch? Could you please elaborate on it? Well, anyone, yeah.
Thomas, would you be more titulated to answer?
Well, I could, but I guess actually Giorgio is the best. But it's quite easy to add infrastructure in Trenissimo at sort of at the level of detail that we need for this. It's basically, you could, if you need an extra track, you copy paste one of the existing tracks. For instance, you can, if you change the speed limit, that's a quick job, for instance. And as long as the computation time isn't killing you, then doing that search again for new and better timetables, given what the new infrastructure that you then have, then that's an okay time spent, I think.
And what would that mean for the optimization side? Would it be able to run on existing solutions, or would you run it from scratch?
But basically, since an existing solution is basically a timetable, you can use that timetable as a desired, let's say, timetable, so as an input as the service concept for the new infrastructure. In this case, with a proper arrangement of the objective function, because we can modify the KPIs which are used for optimization in such a way in which we can foster the adhesion of the resulting timetable to the desired one. So probably I cannot answer to the question.
Okay, well, maybe to wake up Giorgio Medeossi, so he doesn't think we forgot him. So there are some questions about data that you consider. So it's more related to realize the traffic data. So could you say, do you use it? And
Yes.
what kind of processing are you doing? Are you splitting between primary and secondary delays? And how do you implement it further in Treno? Thanks.
Thank you, Nicola. What we do is we import data as we receive them. In some cases, they are received from open data feeds. So overnight stored in our servers, and then morning when you start the tool, you get the update of the day before and so on. In other cases, we receive them as batch files. In all cases, they are imported in Treno and then processed there. As you all know, there are cases in which understanding whether it was a primary or a secondary component is easy, and there are cases in which it is not. So we try to exclude more data, so to be conservative. So every time there is a potential for a delay to have been a secondary, it is excluded. The other important element to remember is that when we are working network-wide, it is one thing. When you're working on a limited simulation area, which is in most cases, because you're typically not replanning the entire country every time, then you need to cut input delays at the border of this area. So the processing has to be redone for the area that you're going to test. That is why it is done in the tool and not before importing data in the tool.
Yeah, sounds good. Sounds good. And we got another question from Herben. Not sure who will be the most appropriate, but it's about shunting movements and shunting possibilities. So we see that they may be actually quite constraining on timetabling. So do you happen to think about it at the strategic level already?
We haven't considered that in the service concepts that we input here. It is, though, what we normally do when we do this in the manual planning is that those shunting movements that are the most limiting on operations, we model those as train sort of parts of the train run, so that we will include those shunting tracks as train tracks and actually run the trains on them as if they did on main signals. And that can also easily be done as part of the input for this optimization algorithm.
Okay, clear. Great. Thanks for that one as well. Well, maybe to see, maybe someone was shy to type the questions, but maybe he's actually more into speaking out. So I would invite anyone who would like to say or to share his thoughts or ideas just to speak out. I see some are prepared.
Hey, this is Stefano Rieppi, Norfolk Southern. I just want to reiterate, I had a chance to meet with TRENOlab over the summer as part of really understanding what some of the newer work is out there in the timetabling arena. I do want to say that I think that this approach has a lot of potential for strategic tabling in general. And strategic timetabling is one of the areas where I think we have huge gaps on the North American scene. Of course, we're rail freight heavy. The trains are very different. Dynamics, timetabling are very different. Our demands are very different. But you know, I wanted to make sure that this audience realized that this is really a new brand brand new approach, I would call it, and it behooves us as a sector on the US side to stay very close to what they're doing, and so I wanted to relay how excited some of us are on the North American side to see some of this work, because we keep tweaking timetables. It's probably the best way to put it, and we never go back to the zero-based approach to saying let's wipe everything out and let's just see what actually makes sense. And so you know, this was a good presentation. The fact that the microscopic simulation and everything else is integrated in one setting is something that you know is new as well, and I think has potential in the medium term. So I just wanted to express my thanks to TRENOlab folks to present, and I really just look forward to seeing how this evolves. So this was more of a common feedback or expression of excitement, but I really appreciate the time this morning. So thanks for getting this together.
Great. Thanks a lot, Stefano. And you brought an interesting question. So maybe for Giorgio is, yeah, indeed, you focus now more with passenger railways, but how do you think about applications for freight or freight-dominated lines?
Thanks, Nicola. Interesting question. In effect, we have been constructing it on, let's say, the Norwegian example. And when we think at Norway, we typically think about, let's say, Oslo or the scenic trains going and routes going to Bergen and so on. But in effect, in Norway, capacity is constrained overnight for freight trains, which need to reach Bergen, Trondheim, and Stavanger before a certain time AM, because they deliver, let's say, goods for supermarkets and so on. So all these lines are single track. So of course, the size of the network is different, but the fact that we need to plan for freight, which is more flexible than passengers, but still it has some constraints, is already there in the studies we are carrying out with the tool at the moment.
Hey.
And also just to comment on Stefano's sort of description here on patching or just adjusting on timetables. That's really what we see here as well. That we have to prioritize away a lot of the alternatives and possibilities that we could have studied when we have to do this manually. So none of my colleagues are afraid to be out of work when we have this fully integrated. Instead, we are excited to be able to actually get on with the backlog that we have with all the alternatives we would have studied if we had the time.
Yeah, Norway is actually more similar than a lot of other European networks to the United States, just because of your single track with sidings. So as you saw some of the visuals today, it's a very common scenario for us, to where you have, here's a 150-mile corridor with 5 sidings, have fun. And here's 10,000-foot trains they got to run 24/7. So there's some parallels there with some of your challenges on your freight heavy lines, especially when you've got the bulk considered. So I feel your pain.
Yeah, and as a follow-up, so now you say you generate a lot of timetables or alternatives. So Matthew Holiday is asking, what about the users and how easy and how much actually time and effort they spend on recognizing the best timetable, or what is their thought process? Is that some more learning that they have to process in order to be able to pick the right one? So could you say something about it?
It's certainly a shift in the tasks that we do. We still do that today, but we would spend a lot less time on creating those timetables and more time on evaluating them. I think that it also makes the integration towards simulation even more important. And that's also a great case for the suite that TRENOlab has here, that it's already set up integrated towards the simulation tool. So the second the timetable is imported back into the timetabling tool, you are set to do a stochastic simulation of each of the timetables. Of course, that's some work to do that as well. But certainly it's actually it is a more sort of demanding task in when it comes to having some experience with timetabling to be able to judge a good timetable from a bad one. But we will free up quite a lot of nitpicking time to do that strategic decision making instead. Well, I for this sort of 1 day loop to work, we also have to work with the rest of the tool chain that our colleagues in the transport modeling do, for instance, so that actually if we can send them 10 timetables in one go and they can do a transport model on each of them and process that quickly, then we can do some of the same optimization down the line as well.
Okay, thanks. And we have Ricardo with his hand up for a while. Hope he doesn't get
Thank
cracked.
you. I'm Ricardo from Syscog, the practitioner, and I have 2 questions. One regards the calculation of running times. In order to compute the train path, you need to know running times, and if you use a running time calculator or other kind of approach. And the second question is regards the optimization. If you have, in order to evaluate the timetable, you also look into the passengers. So if you know how many passengers will travel in a train, so that you can synchronize the departures and arrivals in the best way.
I'll go with a first question then. Thank you. As we have seen, let's say we use the same microscopic model that is used for the simulation, also to compute the running time calculations, which is basically just running one train at a time with a very, let's say, efficient scripting function that first calculates a train on a clean run, then calculates the time losses, so the extra running time for taking all different platforms at all possible stations of the train, then calculates the time loss for stopping the train at all possible platforms, then takes all possible sequences of train paths from all sections of the network and calculates the headway time between trains based on the blocking times of each of them.
Yes,
thank you.
I would add that it is a lot of calculation, a lot of simulation of basically different trains, which is made possible in practical times by the very high performances of our simulation tool. Otherwise, it would take probably a longer time than the actual timetabling algorithm. In order to answer your second question, Ricardo, basically we do not consider explicitly passenger flows within the timetabling process, but it is true that they can be modeled in a feature extension by taking advantage of the connection, which are properly handled by the timetabling algorithm.
Okay, thank you.
And also the passenger flows will, at least to some extent, then be handled by the following up transport modeling, so that their complete travel time from starting station to ending station with changes underway will be considered. But then we at the moment we rely on having input and good connections between the different services. So that's not just sort of discovered post hoc that we messed up.
Thank you.
Yeah, great. Thanks a lot for the really fruitful conversation and discussion. So I'll just stop recording now, but